Welcome back, everyone. I am absolutely thrilled to have you here for this explainer. Today, we're unpacking Unit 4 of Discrete Structures, which means we're diving deep into graph theory and trees. Now, I know, discrete structures sounds like, well, dry, dusty textbook math. But I promise you, what we're looking at today is literally the secret language of the digital universe. It's how computers actually understand the world around us. Okay, so let's jump right in with a question. How does Google Maps actually know the absolute fastest route home during rush hour? Or, think about this, how does a network router know exactly where to send your data packets across the globe in milliseconds? Well, the answer isn't magic. It lies in the exact abstract math we're going to learn today. This isn't just some theory. It is the foundational architecture of real-world software. So here's our roadmap for today. We're going to hit representing graphs, operations, paths and cycles, introduction to trees, minimum spanning trees, and wrap up with their practical impact.
Starting off with Section 1, representing graphs. These are really the atoms of the digital world. In discrete math, a graph is basically just a structure made of vertices and edges. I want you to picture a whiteboard right now. Imagine drawing a bunch of floating dots. Those are your vertices. Now go ahead and draw lines connecting some of those dots. Those are your edges. Put them together and they model pairwise relations. You know, it could be cities connected by highways or computers linked up by cables.
But, as we know, not all relationships are created equal, right? Which brings us to this comparison. We've got basic graphs, and then we have directed graphs, also known as digraphs. In a basic graph, the connection goes both ways, kind of like a two-way street. But in a digraph, the edges actually have an orientation, an arrow pointing in a very specific direction. Think about how followers work on X or Twitter. Just because you follow someone doesn't mean they follow you back. That is a one-way relationship, perfectly modeled by a directed graph. Now, computers obviously don't have eyes to see our whiteboard dots and lines, so instead, that visual web translates perfectly into what we call a 0-1 adjacency matrix. It's simple. If there's an edge connecting vertex A to vertex B, we just slap a 1 in that row and column. If there's no connection, it gets a 0. Setting it up in this grid format is what allows algorithms to compute these relationships at absolute lightning speed.
And this actually leads us to a really fascinating question. What if you draw a circle with a star inside it, and your friend draws two squares connected by a line, but mathematically, they're the exact same graph? No way, right? Well, that's the whole concept of graph isomorphism. Two graphs can look totally different to the human eye, but if they have the same number of vertices connected in the exact same structural way, mathematically speaking, they are identical twins. Moving on to Section 2, operations, paths, and cycles. Let's talk about finding the route. So, the crucial point here is how we move around. A path is simply a route tracing through a graph from one vertex to another. Imagine a little glowing light traveling along the edges. Now watch as that route loops all the way back around and touches the exact vertex where it started. See that closed loop? That right there is what we call a cycle. Contrasting these two is a totally classic exam topic, so pay attention here. Euler graphs versus Hamilton graphs. An Euler path is a trail that touches every single edge exactly once. And according to the math rules we're studying, for an Euler path to even exist, the graph must have exactly 0 or 2 vertices with an odd number of connections. A Hamilton path, on the flip side, is entirely focused on the dots. It's a route that touches every single vertex exactly once, totally regardless of the edges. So just remember, edges for Euler, vertices for Hamilton. And hey, before we leave general graphs behind, we got to talk about planar graphs. The rule here is purely visual but mathematically rigorous. Can you draw the entire graph on a flat, two-dimensional surface without a single edge crossing or intersecting another? If you can untangle the lines so literally nothing overlaps, boom, you have a planar graph. And this is incredibly important for things like designing printed circuit boards in the computer you're using right now.
All right, Section 3, Introduction to Trees. It's time to break the cycle. So, what happens when we completely remove those cycles we just talked about? Well, we get a tree. A tree in discrete math is a specialized graph with two really strict rules. First, it must be entirely connected, meaning no dots are just floating out on their own. And second, it must be completely acyclic. Acyclic basically means absolutely no cycles. By breaking those loops, the whole structure is forced to form a strict top-down hierarchy. Let's ground this academic theory in reality for a second. Why do we even care about trees?
Honestly, because you use them every single day. The file system on your computer's hard drive? Yep, that's a tree structure. Organizational charts in a company? That's a tree. What about the minimax search algorithm used in two-player AI games, which I know is also in your syllabus? That relies entirely on exploring a game tree. These things are literally everywhere in modern computer science. Now, imagine you've got this massive, messy graph full of cycles, but you want to extract a nice, clean tree out of it. That is what a spanning tree is. It's a subgraph, so a smaller part of the original, that touches every single vertex, connecting all the dots, but it strips away just enough edges to ensure there are zero redundant loops. Which brings us to Section 4, Minimum Spanning Trees and Algorithms. This is the ultimate quest for efficiency. We achieve that efficiency through the minimum spanning tree, or the MST. Up until now, our lines were basically just connections. But real life has real constraints, right? What if we add weights or numbers to our edges representing, say, the physical distance in kilometers, or maybe the financial cost of laying down a massive fiber optic cable? An MST finds the one specific spanning tree where the total sum of all those weights is the absolute lowest possible number. And this brilliantly illustrates how computer scientists actually solve this problem in the real world. They use algorithms. Your syllabus focuses on the two most famous ones for this, Prim's algorithm and Kruskal's algorithm. Now, they both arrive at the exact same minimum spanning tree, but their core logic is fundamentally different. Prim's grows outward locally from a single starting point, while Kruskal's is kind of greedy. It hunts for the shortest edges globally across the entire map. Let's look a bit closer. Here is Prim's algorithm step by step. Think of it as a procedural story of growth. Step 1. You drop a pin on any starting vertex. Step 2. You look only at the edges directly connected to your current tree and find the one with the absolutely smallest weight. Step 3. You add that edge. And step 4. You repeat. You're slowly spreading outward like a puddle of water, always taking the cheapest immediate step until every single dot is connected. Now, contrast that with Kruskal's algorithm. Kruskal's really doesn't care about a localized starting point. Step 1, it gathers every single edge on the map and sorts them all from lightest to heaviest. Step 2, it picks the absolute shortest edge anywhere on the board. Step 3, it adds it, but with one massive rule: only if it doesn't create a cycle. Like I said, it's greedy. It just keeps grabbing the cheapest edges, wherever they are, and stops exactly when it has added n-1 edges, where n is your total number of vertices. And finally, Section 5, Conclusion and Summary. Let's look at the big picture. Okay, here's your rapid-fire Unit 4 recap to really lock this into your memory. Vertices and edges represent relationships. We use 0-1 adjacency matrices so the computer can actually compute the map. We use Euler and Hamilton paths to define our routes through that map. We break the cycles to create hierarchical trees. And finally, we use Prim and Kruskal's algorithms to optimize that entire network for maximum efficiency. So the absolute most crucial takeaway from this explainer is this. When you are drawing dots and lines on a whiteboard and tracing these algorithms, you are not just doing abstract math. You are literally learning the structural backbone of computer science. This exact logic is how social networks recommend friends to you, it's how your GPS navigates traffic, and it's how the entire internet routes data. Algorithms like Prim's and Kruskal's have been around for decades, built on math that is literally centuries old. But as artificial intelligence and neural networks become infinitely more vast and complex, how will these fundamental graphing techniques evolve to map the AI systems of tomorrow? It is such a fascinating frontier, and you now have the tools to actually understand it. Thank you so much for learning with me today. Keep exploring, and I'll catch you in the next explainer.